What's up, guys? Welcome to this video on logarithmic decrement. Okay, so let's get into it. It's quite an easy concept. There's two main formulae to follow, and yeah, nothing much to it. Okay, so the focus that we're going to be focused on underdamped systems. Okay, and they are going to be undergoing oscillating motion. Okay, basically. Let's draw our graph. So it's going to be somewhat of a sinusoidal graph, and it's going to look, let's say, something like this, where the amplitude is constantly decreasing. And we have our displacement time graph, and this point right here is going to be, let's say, x0. Then the next point is x1, and the next peak is going to be x2. Okay, and similarly, I'm going to have the times t1, t0, t1, and t2, and obviously this continues, but I'm just going to go three times. Okay, basically what logarithmic decrement basically says is that if we look at consecutive displacements, so displacement x0, x1, and x2 are all consecutive, they will happen one after another, we can actually determine the damping ratio with only knowing the displacements and the times. Okay, and there's two main equations. So the logarithmic decrement, that's the symbol for it, is equal to 2 pi c, or damping ratio, over the square root of 1 minus c squared. And this is equal to 1 over p ln of x1, or our first displacement, over xp plus 1. Okay, so you might be asking what p is, and we can say that p is the number of cycles. Okay, so for example, if we're going from here, that's our first cycle right there, so that would be p equals 1 cycle, and this would be p equals 2 cycles. Okay, yeah, so that's about it. That's okay. Wait, we do have one more formula. Let's write this down. So we can also have c in terms of c can also be written in the following form. So our damping ratio is equal to the logarithmic decrement over the square root of 2 pi squared plus logarithmic decrement squared. Okay, and all of that is under the square root bracket. Okay, knowing that, we can actually go straight into an example. Okay, so let's do, okay, so we have an example. Okay, so working with the example, we have been given the following system. So it's quite a very easy, simple system. We have a spring, we have a damper connected to a cart of mass m, and we have some displacement x. Okay, at the same time, we've also been given a graph. Okay, let's say k and c. At the same time, we've been given the logarithmic, or the displacement time graph. So I'm going to say that's the st graph, and the graph looks something like that. Let's see if I've got enough. 1, 2, nope. Let's make this graph a little longer. Okay, let's stop somewhere there, and that's t. Okay, and we have x0, x1, x2, x3. Okay, and we've been given two timestamps, 0.25 seconds, and t3 is at 0.75 seconds. Okay, and we also know that x1, let's make that look better, x1 is equal to 0.6 meters, and x3 is equal to 0.4 meters. Okay, and we want to find the displacement at A, and before that we want to find the following properties. Let's say we want to find the logarithmic decrement, we want to find C, and we want to find the damping constant as well. Okay, so let's start out. Okay, I've been really bad with this, and I've been doing answers and solutions in the same color and messing that around, but I'm going to try to be better. So I'm going to do solutions in red and questions in black. Okay, so looking at the solution, let's start with our equation of motion in terms of x, and I'm going to say the equation of motion just by inspection because it's quite simple. It's going to be mx double dot plus cx dot plus kx is equal to 0. Okay, we've also been given some other information on the side, and we've been given that mass equals 5 kilograms. That's not right. We could say mass equals 5 kilograms. K is equal to 400 newtons per meter. Cool stuff. Okay, so let's start out by finding our logarithmic decrement. There we go. C is equal to, I'm going to use the formula because we have this system right here. That would be P is equal to 2. I'm going to use the equation that goes as follows. And it says the logarithmic decrement is equal to 1 over P ln of x1 over xp plus 1. So our P, like I said here, it is 1, 2. So it's going to be 1 over 2. Okay, ln of x1, this one right here, which is 0, 6 over P is 2. So basically we go once, twice, and we've got this value right here. So 0.4. And that is equal to, let's see, 0.202733, let's say. Okay, and I'm going to store this in my calculator as A. That just makes it easier instead of continually writing out those numbers. Okay, so that one's done. Next we want to find C, and luckily we've got a very nice equation that we can use. That's quite simple. That goes that C is equal to the logarithmic decrement over 2 pi squared plus logarithmic decrement squared. So this I'm going to just write, like I said before, I stored this as A, so I'm going to say this is A over 2 pi squared plus A squared, and that's going to give me the following answer. (0.03225). Okay, and that is unitless, and this is less than 1, therefore the system is underdamped. Okay, and like I said before, this works for underdamped systems. So that works out quite nicely. Okay, so we've got that as well. So now we need to know what C is. C, okay, we know we can work out as being, or we can rather write the equation in its original form. So the damping ratio is equal to C over 2 square root of K equivalent M equivalent. Okay, so we know this damping ratio, and this damping ratio I'm actually going to store as B. Okay, storing stuff in your calculator makes life a lot easier. Okay, and I'm going to say that C equals 2 times the damping ratio square root of K equivalent M equivalent. Okay, now what are these values? Okay, I'm going to say it is 2 times B because I've stored it right there. Our square root of K equivalent is that right there. It's just the value of K, which we know is 400, and M equivalent is just the value of M, which we know is 5. Okay, so putting that into our calculator, we get the following answer. C is equal to 2,88445. Okay, Newton seconds per meter. Okay, cool stuff. So now we've got that. Now we just need to figure out the displacement at A. Okay, so for the displacement at A, we're going to work backwards. I'm going to change colors because then it might make a bit more sense. So we know what the logarithmic decrement is basically, we can assume it to be a constant. Because our point A, or the point that we're looking for, A is this point right there, which is x2. So we're actually looking for A or x2. Okay, and the logarithmic decrement is a constant from this point here all the way to this point there that we measured. Okay, so we've got C. Okay, we know that from this point here, from x1 to x2, p is equal to 1. So I'm going to say p equals, okay, so I'm going to say that we know p rather. We know p. x1, again, is that value there, which we know, and x p plus 1 is the unknown. Okay, so basically we can write it as the following. So the logarithmic decrement, which I stored as, okay, let me just write out the number now, 0.202733 is equal to 1 over 1, which is just 1, okay, times ln of 0.6 over, I'm going to say x2 because that is what we want. x2. Okay, what we're going to do is we're going to raise both sides to the power of e. So what we're going to have is e to the power of 0.2027333 is equal to 0.6 over x2. So we can solve for x2. Let's see what it comes out as. Okay, and the answer is 0.489. Let's take it as 9898 and units of meters. Yeah, so that's our final answer, and that is between, so I'm saying that this is 0.489898, which is between 0.4 and 0.6. So that actually makes a little bit of sense. Yeah, so that's basically all I really want to go into. There's nothing too difficult there. You just need to know how to use the formula and you need to understand what they mean. Yeah, so I hope this short, nice, succinct video was good. Thanks for watching, guys.